Welcome everybody to this second webinar where we're going to talk about CPT versus SPT. What I'm going to talk about, but before I do that, let's give you a few disclaimers. First of all, I'm a Dutchman. I live in North America. I've moved here permanently in 1999, but I was born and raised in the Netherlands. I got my education in the Netherlands, and that means that when I talk about soil investigation methods, CPT is clearly the preferred soil investigation method as far as I'm concerned. I'm a true conehead, as you can see here on the screen. But in these CPT webinars, I will try not to be biased. I will try to give you objective and honest information about CPT, because there is no such thing as a perfect soil investigation method, or any test method for that matter. Everything has its pros and cons, and as long as you're fully aware of that, you can pick the right one. What are we going to talk about today? We begin with a short introduction of both CPT and SPT, a little bit of the history, what it's all about, and then I'm going to look at these two test methods from three different angles. And I've titled those 1 versus 3, intermittent versus continuous, inconsistent versus consistent. And once we've talked about these items, you will probably understand more clearly why I picked these ones. You could look at these test methods from all kinds of other different angles, but then since we are trying to limit these webinars to 25 minutes with a little bit of Q&A so that we don't exceed the half an hour, that's about all the time that I have, and then we'll come to a conclusion, and we ask you then to give your opinion again through a second poll. So let's get started with what is CPT. What you see on the screen on the left-hand side is a kind of a graphical representation of pushing a cone into the ground. In this case with a cone truck, a 20-ton truck, but you don't need to do it with that heavier truck. You can do it also with a crawler. You can do it even with a mobile unit. The whole issue is that you push an instrumented cone into the ground, and you do that at a speed of 0.8 inches per second, or 20 millimeters per second. That's important because what we try to do is have a consistent reading, so everybody around the world does it with the same speed. Although, since the code allows you to go a little bit faster to 25 millimeters per second, people generally increase the speed to close to the upper limit, simply because it then takes less time to do the test. And during the test, you record the tip resistance, the sleeve friction, and the pore pressure. So you get 3 data points, and that is being recorded every 10 millimeters or 0.4 inches until the cone reaches the target depth or refusal, because sometimes you cannot just push the cone any deeper. So that, in a nutshell, is what the CPT test is all about, and it's described in ASTM D5778, which is going to be reissued, by the way, in the next couple of weeks. We just got it approved within ASTM. A little bit about the history. Back in the 1930s, Peter Barense in the Netherlands developed the cone as part of a project for the Dutch railroads. They were looking at soil characterization and the bearing capacity of soil, and had to come up with a new method, and they came up with the cone penetration test. At that time, very simplistic, one metal piece, cone-shaped, was pushed in the ground by hand. And that gave you an indication of what the bearing capacity was of the soil. Then in the late 1950s, the hydraulic pushing rigs were developed, first for 10 ton, later for 20 ton. So you no longer had to push it by hand, but we're still talking about a mechanical cone, no moving parts. That changed in 1965 when Begeman added a sliding sleeve to measure the sleeve friction. And that was then the friction jacket cone, and that is commonly referred to around the world as the Begeman cone. But it was still a mechanical device. And then in 1971, so more than 50 years, or almost 50 years ago, we came up with an electric cone penetrometer where the tip resistance, the sleeve friction, and the pore pressure are measured electronically, and those signals are sent to the surface. So really, the method has been around for about 90 years. And the method that we're using right now, electrical CPT, has been around for about 50 years. What is an SPT? For those of you that are in North America, you may wonder why I give this introduction. but there are many people around the world that don't use SPT as frequently. So I just briefly go through a similar description. Basically, what you do is you drill a hole, a borehole, and then at the clean-out depth, you put your split spoon, which is a cylindrical sampler that can be taken apart into two parts, so that you can take the sample out. And you first drive it 6 inches or 150 millimeters into the ground to get it seated. And then you drive it another 12 inches or 300 millimeters, and you count the number of blows that are required to achieve that. And that's the so-called N value. And you do that by dropping this hammer 140 pounds, standard weight 63.5 kilograms. And you can already see, based on the odd number of kilograms that it was developed here in North America, you drop it from a height of 30 inches. And you just count how many blows it takes to get that sampler another 300 millimeters or 12 inches into the ground. And that's this so-called N value that you often hear. A little bit about the history. It all started in 1902 when Charles Gow came up with a sampler, a 1-inch sampler. So it's not the sampler that we're using right now, today, but he started making these samplers and do exploratory borings to get samples out of the ground. Then in the 1930s, that sampler, the dimensions of the sampler were standardized by Harry Moore, and it really was not all that popular until in the late 1930s, Carl von Terezaghi and Arthur Casagrande, two really legends in the geotechnical world, both from Austria, who had moved to the United States early in their career and started working here. They promoted the adoption of this split spoon sampling procedure. And because those two guys, those two legends said you should start using it, it really became very popular. And it was roughly around the same time that CPT was developed, or slightly later, but in the 1930s. But at this time, SPT was still a sampling method. And it was not until the late 1940s when Terezaghi and Moore started using this method to find a correlation between the blow counts and the bearing capacity. And it's when SPT really became a methodology to figure something out about the bearing capacity of the soil. So in effect, from that point of view, SPT is a newer method. Has not been around as long as CPT, which is often viewed the other way around. So now you know what CPT is, you know a little bit what SPT is, and let's now look at those two methods side by side. And the first characterization that I would like to use, I want to call it 1 versus 3. And on this screen, you see some kind of a graphical representation to illustrate that point. You have 1 SPT and you have 3 CPTs. And what do I mean by that? Let's look at the objective of a soil investigation method. When you're doing a soil investigation method, you're not interested in what the soil is. It may sound weird, but I really can care less whether the soil or the color of the soil or what soil type you necessarily have. You want to know what is the behavior of the soil. You want to know whether it behaves like a clay or like sand, like a granular or like a cohesive soil. And more importantly, you don't want to necessarily just know how the soil behaves. You want to know how the soil behaves when it comes to interacting with the foundation. Sure, you can use CPT with dissipation tests for some other things as well, but the primary use of SPT and CPT is to figure out what the bearing capacity is of the soil for a foundation. So what you're interested in, and that's why it's so big here, is this arrow between the soil and the foundation. You want to know what the interaction is between the soil and the foundation, and to characterize it, you want to know how the soil behaves. Problem with that is that it's not that easy to describe how soil behaves. And what you see here on the screen, on the left and on the right-hand side, one for clay and the other one for sand, is a whole bunch of different parameters that describe how soil behaves. And the objective then of the soil investigation method is to get information about that. When you then look at SPT versus CPT, with SPT, you basically get one bit of information, the N value. With CPT, you get 3 bits of information, the tip resistance, the sleeve friction, and the pore pressure. And those three parameters, or that one parameter, you then need to utilize to come up with correlations or functions to describe all those other parameters so that you get a good understanding on how the soil behaves. Obviously, if you have three parameters to start with, you can have a more accurate correlation, a more accurate description of the soil behavior than when you have to deal with only one. And that's why I've titled this section 3 versus 1. But sometimes you can have even more than just 3. You can go to 4 if you add a seismic module behind your cone, and then you have the shear wave velocity as well. Yet another parameter to understand on how the soil behaves and therefore get a better characterization on the interaction between the soil and the foundation. So that's the first aspect, 1 versus 3. The second one I've called intermittent versus continuous. And again, on the screen you see a way on how to visualize that. You see CPT, one after another, CPT, 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 where with SPT, it's kind of spread out over the screen and kind of a straight line in between the letters. Now, what do I mean by that? If you were here in my office right now, and from behind my desk, look to your right, you see these two doors with windows in there. And if a Mr. CPT would be sitting behind my desk, he would say, well, hey, it's nice that you can look outside from behind your desk and look at the trees. Well, if SPT would be sitting there, his comment would be, well, it's too bad. you cannot look outside from behind your desk. And you might wonder, well, what do I mean by that? Well, the distance of the width of those two doors is slightly less than 5 feet, slightly less than 1.5 meters. And the thing is, with CPT, you record data every 0.4 of an inch, every 10 millimeters. And that means that you don't miss anything. And therefore, as the CPT is scanning that wall, it sees the windows and it can look outside. With SPT, it gets a data point every 2.5 or every 5 feet or something like that, every 0.75 meters to 1.5 meters. And if it just testing every 5 feet, it would look at the left of these doors, it would look at the right of the doors, it would see no windows, it would assume therefore that in between there is no window because it's just the same data point that you have on either side of the window, and therefore he cannot look outside. In other words, CPT catches every detail, and SPT not only uses a sampler, but really samples data points and then just hopes for the best to try to come up with data in between, or a characterization in between those data points. Now, that's obviously not realistic. There is no Mr. CPT, there is no Mr. SPT. So let's look at a more real illustration of this whole thing. What you see here is a graph that I took out of a report by Han Prezzi and Salgado. It has nothing to do with what they were trying to do, but it's just a good illustration of my point. What they did was an SPT and a CPT, two of each, very close together to get an indication of what the bearing capacity was. On the left-hand side, you see the blow counts, and the right-hand side, you see just the tip resistance. And I want you to focus on this area between, say, 6 and 9 meters. And you see 3 data points there. And pretty much what they have done is draw a straight line in between, and it kind of looks like a continuous reduction of the bearing capacity. Yet when you go to the CPT data, you see much more detail. You see that there are quite a few peaks in there, and it's not just one straight line going down. And that is only with the tip resistance. If you consider that with CPT, you also get information, the sleeve friction, and you're going to get information from the pore pressure, and you get not only a continuous profile, but you get also all kinds of parameters of that profile. But it's obvious that you are no longer just looking at individual data points that you then just connect, but you have a continuous profile, and that's why intermittent versus continuous. And that's kind of the second angle that I want to look at this whole thing. But I told you I will not, or try at least not to be biased, because a CPT cone cannot be pushed through every layer. Sometimes the layer is simply too hard. You cannot push a cone through concrete. Many people try it and continue to try it, and they fail every single time. you cannot push a cone through certain rocks. You need to pre-drill it. And in those cases, obviously, you don't have a continuous profile. But as long as you can push the cone through something, and most of the time when you can push a split spoon down, you can push the cone down, as we saw last month, you have a continuous profile. So that's the second angle. The third one is a little bit more complex, and I have called it inconsistent versus consistent. And what you see on the screen is 5 or 6 times the word CPT, all the same font, same size, same everything. And SPT also on the screen in different colors, in different fonts, underlined or not, different sizes, different everything. And it kind of illustrates the point that I'm going to make when you look at these two methods. First of all, consistency is key. What you want is a soil investigation method, whether you come today or tomorrow, whether you do the test or your colleague does the test, that it is consistent. Because only if you have consistency, it's not only key, but it's also key to success. If a method is not consistent, it really is not a successful method that can be applied or should be applied. So let's go back to CPT. You've seen this illustration at the beginning. I want to go back to that, and I want to highlight a couple things in there. First of all, the cone that you push into the ground is 100% standardized and defined in the standards. And it's not just defined in ASTM D5778, as you see on the screen. The ISO standard does exactly the same thing. And with this new edition of the ASTM standard, ISO and ASTM are pretty much on the same page, same dimensions. What you see there is that the length of the sleeve friction, the surface area of the sleeve friction, the diameter of the cone, the diameter of the cone tip, the height of the cone tip, the angle, everything has been standardized. And also we push it into the ground at a standardized rate. So we really make sure that everything that you have there is completely standardized. But on top of that, what you do is before you start the sounding, not or at the beginning of the day or the beginning of the week. No, at every sounding, before you start your CPT test, you do a calibration test of your cone. You check that the cone is still within the calibrated values. Then you do your CPT test. And then when it comes out of the ground, at the end of every sounding again, you check that calibration again. So that you can very confidently state that at the beginning of that test, the cone was in good shape. That during the test, the cone did not get damaged because at the end of the test, it was still in good shape. And that's how you know for sure that you have good, consistent data. And then finally, as I mentioned already before, that penetration speed is not only defined, it's also continuously monitored and recorded. And what you see here on the screen is a control panel of the GeoPoint data acquisition system for CPT, and it's kind of hidden on the bottom right-hand side. But as you are doing your CPT, you continuously see the unit there, and you also see the velocity shown here is 2.25 centimeters per second, so 22 millimeters per second, slightly more than the standard 20, but within the standard because the standard allows 25 millimeters. Not only is this recorded or is shown on the screen, it's also recorded in the data file so that when you see the data later on, you can make sure that it was indeed adhered to. Now, let's go look at SPT. You drive that split spoon into the ground by dropping this hammer, but the problem is not every hammer is the same. And some hammers put in about 45% of the potential energy in the ground. Sometimes it's 95%. And it also depends on what kind of method I've used to drill the borehole, whether I have a liner inside the split spoon, all kinds of differences that make it possible to have an inconsistent reading. So what they have done now is to try to come up with some kind of a standardized version, and that says that you are using not the N value, the recorded number of blows, but the N60 value. And what the N60 value is really what you see here is a simplified equation where you take the hammer efficiency, you take the borehole diameter, correct that, you take this, the sampler, whether it's a liner or not, you take the number of rods, because if you have a longer rod string, more energy gets absorbed by those watts, and then you get your uncorrected blow count, and then you come up with some standardized N60. And that, to a large extent, will correct for all those variances that you have, but not for all. There are other elements other aspects in there that make it very hard to figure out what is really the standardized value. And then again, that N60 value is not always recorded because you only record your measured value, and all the details may not be around. So therefore, it's very difficult to say that you have a consistent result when it comes to your SPT readings. And that's why my conclusion is that SPT is really inconsistent versus a consistent reading of your CPT. But let's go back to that same graph that I showed you earlier, this time looking at the depth, say, between 11 and 14 meters. Again, I told you, you have 2 tests done in the same location, same equipment, same operator, same everything, which means that you should get pretty much the same results. Now, soil is never 100% the same. Sometimes you have some slight variations, and you see in the right-hand side the graph for the cone resistance. Those 2 lines don't necessarily overlap each other 100%, but it's very similar. You can clearly say, yeah, those 2 things are the same. The left-hand side, you see the blow count with the SPT, and you see that at around 12.5 meters, I have 2 readings, one a blow count of 30, the other a blow count of 60. Now, the rest of the graph, pretty much, except for near the surface, where you also have big variances, but the rest of the graph looks more or less the same. But you see here that you have about 100% difference between the low and the high value. That, to me, is another clear illustration that an SPT test is not necessarily providing you with consistent results. So, with that, and given that I'm about 25 minutes past the top of the hour, I'll come to my conclusion. Obviously, I prefer CPT. It's an efficient, it's exciting soil investigation method. Has been around for a long time with good correlations, but more importantly, for the purpose of this presentation, it provides a consistent answer. It provides a continuous soil profile. At the same time, don't take me wrong. I don't say that CPT is perfect. I'm excited about it, but it's not perfect. Every test method, as I said earlier, has its limitations. Sometimes the soil is too hard, and then you cannot push the cone through there. Therefore, you don't have a continuous soil profile. But as long as you're aware of what those limitations are, you are in good shape. With that, I'm at the end of the presentation. Troy, are there any questions that have come up during the presentation?
Yeah, Gerald, there was one. John had asked it, John Lincoln. He was wondering about combo rigs that can easily do SPT and CPT. Is there a spreading in the use of CPT, or zero, little, some? What have you seen out there, Gerald?
There are obviously people that are doing, especially here in North America, that are doing quite a bit of SPT. That's what they're used to. That's what their clients describe quite a bit. And then they want to slowly move into CPT. And then you can use on those rigs, do CPT as well. Sometimes it's very efficiently done, very accurately. Sometimes it's not that accurately. The biggest problem with a CPT on an SPT rig is the limit that you have in the dead weight. Most of the time, you do it at the end of the truck, just where your drilling drill head is, and that means that you only have the weight on the rear axle as the dead weight. So you have a limited amount of capacity that is available, but it's an easy way of moving into CPT, and you get perfectly solid results from that.
Okay, thanks. What about, there's another question. What would be the hardest soil you can get through in terms of Q?
I would not necessarily mention it in the form of a Q. I would characterize it differently. Because the soil is this kind of, again, there are different names to the soil, but if you consider that if you are having an SPT blow count of 100, and mind you, most of the time when you do an SPT test, you go to a blow count of 50 plus, and then you say, that's enough. If you have a blow count of 100, and you have a 20-ton truck, you can still, with a 15 centimeter square cone, you can push that cone through there. Which means that you can, softer rocks, you can go through there. Stiff sands, you can go through there. Even gravelly sands, you can go through there. If you have a large boulder in there, you will not be able to push your cone through. If you're a landfill and you have some piece of concrete there, you cannot push your cone through. But softer, weathered rock, you might still be able to push your cone through. But generally speaking, more importantly, if you're going to get a split spoon down, you can get your cone down.
Okay, I did want to point out too that some of the other webinars that will be given, one of those is going to be on the Sonic CPT cone, which is a cone that is unique that we came out with, that a lot of times when you are pushing your cone and you hit a hard layer and you've hit resistance, we now have developed a cone that you can put sonic vibration on that to get through that harder layer to continue your push.
Thank you so much for participating in this webinar, and we look forward to seeing you guys next month.